Hello dear student, Assalamu alaikum. Welcome to the course of Electric Machine 2, lecture number 11. Today we are going to study the synchronous condenser, hunting, application of synchronous motor, and comparison between induction and synchronous motor. So, synchronous condenser. We know that synchronous motor take a leading current when our excited and therefore behaves as a capacitor. In our excited synchronous motor running on no load is known as synchronous condenser. For synchronous condenser, let's see a diagram and figure. This is the three-phase load, and we have a three-phase synchronous motor connected with it. IL is the load current, IM is the current from synchronous motor, and I is the current in the three-phase system. So we take voltage as a reference, and we know that mostly the load is inductive, so the IL current will lag behind the voltage. So this is the IL current which is lagging from the voltage. And we also know that we are using synchronous motor for improving the power factor, and when working at no load it has a leading current. So this is the current that is for synchronous motor. Now the resultant of these two current IL and IM is I. Resultant of IM and IL is I. So we see that it lag behind the voltage by a lesser angle than IL. So in this way, as shown in this vector diagram, the power factor is improved. So it is described here that in the figure the power factor improvement by synchronous condenser method. The three-phase load take current IL at low lagging power factor cos angle L. The synchronous condenser take a current IM which leads the voltage by an angle this. The resultant current I is the vector sum of IM, the synchronous condenser current, and IL, the load current, and lag behind the voltage by an angle this. It is clear that angle is less than load angle, so that cos, that is the power factor, is greater than cos of the load. Thus the power factor is increased from load, that is when we are not using a synchronous condenser, to a new angle that is in improved power factor. So this is one of the application of synchronous motor, that we are using this in the system, in a three-phase system, to improve the power factor. Next is hunting. We know that when a synchronous motor is loaded, its rotor fall back in phase by the coupling angle alpha. We already studied that whenever there is an increase or decrease in load, the angle that is between the rotor and the rotating magnetic field change. So in a synchronous motor, when it is loaded, the rotor fall back in phase by a coupling angle alpha. As load is increasing, this angle also increase so as to produce more torque for coping with the increased load. If there is a sudden decrease in the motor load, the motor is immediately pulled up or advanced to a new value of corresponding to the new load, that is a new angle. But in this process the rotor overshoots, and as it is rotating with some speed, and hence is again pulled back. In this way the rotor starts oscillating about its new position of equilibrium corresponding to the new load. The amplitude of these oscillations is built up to a large value and may eventually become so great as to throw the machine out of synchronism. So hunting is a process that is in the machine and is used, and it is due to this reason it throws the machine out of synchronism because of increase or decrease in load, and the rotor is out of synchronism. Now the application of synchronous motor. There are some application of synchronous motor. The first one is the constant speed application. We know that a synchronous motor running at a constant speed, that is a synchronous speed. So because of high efficiency and high speed, synchronous motor about 600 rpm are well suited for load where constant speed is required, such as centrifugal pump, blower, rubber and paper mill, etc. Low speed synchronous motor, that is when the speed is less than 600 rpm, are used for drivers such as centrifugal and screw type pumps, vacuum pumps and metal rolling mills, etc. So these are the things where synchronous or constant speed motor is required, and we are using synchronous motor. Now the next one is voltage regulation. The voltage at the end of a long transmission line vary greatly, especially when large inductive loads are present. As we know, the mostly of our loads are inductive. When inductive load is disconnected suddenly, the voltage tends to rise considerably above its normal value because of the line capacitance. As we know that in transmission line we have inductive property, capacitive property and resistive properties. By installing a synchronous motor with a field regulator for varying its excitation, by varying excitation we can achieve leading, lagging and normal power factor. This voltage rise can be controlled. When line voltage decrease due to inductive load, motor excitation is increased, thereby rising its power factor, which compensate for the line drop. On the other hand, line voltage rise due to line capacitance effect, motor excitation is decreased, thereby making its power factor lagging, which help to maintain the line voltage at its normal value. The next one is power factor correction. We studied in a synchronous condenser. Our excited synchronous motor having leading power factor are widely used for improving power factor of those power system which imply a large number of induction motor and other device having lagging power factor. So this is for power factor correction, as we studied is a synchronous condenser, and we use our excited synchronous motor for this purpose. Now this is the comparison between synchronous motor and three-phase induction motor. The first one is the speed. We know that the speed of synchronous motor remain constant, that is ns, from no load to full load. And in induction motor, the decrease with load. When we increase the load, the speed decrease. Power factor can be made to operate from lagging to leading power factor by changing its excitation. And three-phase induction motor operate at lagging power factor. Excitation is required in the synchronous motor and no excitation for the induction motor. Synchronous motor are economical for a speed below 300 rpm and economical for a speed above 600 rpm, the three-phase induction motor. And synchronous motor is not a self-starting, and that is we required some arrangement for this, and induction motor is self-starting. The construction of the synchronous motor is complicated as compared to the induction motors, and the starting torque of synchronous motor is more as compared to the induction motor having less starting torque. So thank you for today's lecture.